We started out chapter 14 with the valence bond theory, so we're talking about bonding for molecules. And we started out with the valence bond theory, and we're still messing with just diatomic molecules. And they moved from the valence bond theory to the molecular orbital theory, where we had this back to our quantum mechanical idea of wave functions and how they came up with their wave functions. One method is the LCAO, linear combination of atomic orbitals. And these solutions to the Schrödinger equation for the hydrogen atom were the atomic orbitals, that's your phi. And that's what the electrons are placed in, all these atomic orbitals. And then little c is a weighting factor. And you add that linear combination up and you get your wave function. You may not get the right energies, but if you just modify your c's, you can get pretty much the right energies. So when you use those wave functions, and you generate energies, here they are. They're trying to put them in a table, in a diagram, called the molecular orbital energy level diagram. And a lot of times what they don't show is the stuff that I think really helps. Like, for example, here we're talking about a hydrogen molecule. So that means you've got diatomic, right? H on each side. So that's what they do. They put each atom on each side, one on the right, one on the left, and they put all of this atom's atomic orbitals and all this atom's atomic orbitals. So they're both hydrogen, so they both have a 1s, and they're both lined up perfectly in height, so that because of the same energy, right? Because you wouldn't have one s higher than another 1s. They're both 1s, and they're each contributing 1 electron, so you have 2 electrons. So you see two arrows there, and if you start with 1, 2 orbitals, atomic orbitals, right? You do the math, you end up with 2 molecular orbitals. One of them has a star, the other one doesn't. So the one with the star we're supposed to call antibonding. But I think what I like about these diagrams is it shows that it would make more sense for these electrons to be in the separate atomic orbitals, not even form a bond in the first place in comparison to being in an antibonding, because there's higher energy. So whenever you see any molecular orbital with a star on it, it's always higher than the constituent atomic orbitals you started out with. Always higher. That's what makes it antibonding. And if you don't see a star, it means it's bonding. It's always lower than the constituent atomic orbitals you started out with. Kind of makes sense. So I kind of like the height idea rather than just looking at these stars. You didn't really need them. You just kind of look at the height in your molecular orbital diagram. But, you're not going to want to go through all this work drawing all this stuff all the time. Okay. So here we have a helium molecule. Diatomic, homonuclear helium molecule. So we're talking about He2. Something that exists or doesn't exist. You ever hear of this? He2? No. I've heard of H2, right? That sounds familiar. He2, not so much. So each helium contributes like 2 electrons, 2 valence electrons. You have 4 total. But you've got constituent 1s, add them up, a bonding, and an antibonding. Okay. So in this molecular orbital theory, we have something called bond order. And again, this entire discussion is all about diatomic molecules. And they give a little symbol B for bond order. So I guess the bigger this B is, would you expect longer bonds or shorter bonds? What can you infer? Bond order. To me, it sounds like a bigger bond order. I mean, hey, more bond, right? More interaction. Stronger bond, so the bond should be shorter in length. That's how I kind of look at it. But how do you calculate this bond order? Well, 1/2 times n minus n star. Guessing, what do you think n and n star are? star, I think, is the big hint, but
The number of electrons in the bonding.
yes.
Minus the electrons in the anti.
Exactly. The number of electrons in the bonding minus the number of electrons in the anti-bonding. So for, what would be the bond order of a hydrogen molecule? It would be
1.
E equals 1. What would it be for a helium molecule? Diatomic homonuclear helium molecule. 0. Right? So it kind of follows. It doesn't exist. Bond dissociation energy, we kind of already talked about it. I don't know why it's even here again. Right? It's the energy to do what? Alyssa, what would be it? This is the number of kilojoules you would apply to do what to that bond? Break it. Exactly. Bust it apart. Okay. Free those electrons. Pi orbital. I don't know why we're rehashing this, but that's where you have a what plane between the overlap? We called it a overlap here, overlap here. There's nothing here. I tried to draw a plane. Remember, that's my idea of drawing a plane, this flat rectangle. There's a nodal plane between the overlap. Okay. And finally, they gave us a nice picture of a pi orbital. It's actually a cylinder. Okay. Usually you're going to get, I'm not sure, I think the book was talking about p orbitals, right? If they're oriented the right way, you can get these pi molecular orbitals. Or p and d, sometimes p and d orbitals also will. If they overlap, if you pick the right ones, you can get pi molecular orbitals. But not really a whole lot there. But the idea is you're picking these different orbitals, and there's overlap. I mean, that if you want there to be a bond, well, then you need these orbitals to overlap. That's why we pick, oh, this p orbital is lined up with this p orbital, so we have overlap. So what they're trying to say is, let's go back to the Schrödinger equation. Let's go back to wave functions. And what they're saying is the overlap integral. They gave it a big letter S. And I'll just write a general way of saying this. Okay. Now, we've done some homework, and we just did the homework, where we had these two wave functions in the integral, d tau, integrating over all space, and we said, oh, they're different. So we set it equal to 0. That's the technical word is orthogonal, where there's absolutely no overlap at all. They're just essentially, wow, perpendicular. There's only 2 dimensions. But the point is there's no overlap at all. There's no positive area overlap. But that's just one extreme. I mean, you can go from the extremes. You can get 0, and the word would be orthogonal. You're right. Extremes are S is 0. That's the word orthogonal. They're absolutely, completely different wave functions. There's no overlap at all. There's no similarity at all. And the other extreme would be the number 1. The wave functions are what? They are the same. So there's the other extreme. 1. Here's where they're the same. I guess orthogonal. Completely different. I don't know what it's hard to put language to this because we're talking about 3 dimensions. You got to be thinking about 3-dimensional space. Okay. So that's where they're getting at, overlap, and how you can have different bond energies then. So in drawing these molecular orbital energy diagrams, in drawing these molecular orbital energy level diagrams, pretty much all you got to know, it's almost like that Aufbau building up principle, right? Except there we had, 1s, and then 2s, and then 2p, and then, remember this, Alyssa? 3s, and we kept going up. Okay, we're not talking about atomic orbitals anymore. Now we're talking about, okay, let's take these atomic orbitals, make a linear combination of them, get some wave functions, generate their energies, and then we name them. And so what are we going to name them? Here they are. So depending on, now this is where it gets kind of confusing. Here's the answers, right? This guy, we're going to use this a lot because this tells us the order to fill in these atomic orbitals, to fill in these molecular orbitals. And notice how pi, there's really actually 2 there all the time. There's actually 2 orbitals. That's why you can fit 4 in there. Okay. But I think what I'm trying to get at is they're giving the answers for Li2, Be2, on up, right? They're giving you the answers for all those. But this is really a generalized plot because what you're supposed to realize, I don't know if the book hits this hard enough, is if, let's say you pick nitrogen. So nitrogen has how many valence electrons? 5. Each nitrogen has 5. So that means 10 total, right? So we've got 10 electrons. If you have something else that has 10 electrons, what was the word for that? Another molecule. Count up all those electrons, and you get 10, but it's not N2. What was the word for that?
Isoelectronic.
Very good. Isoelectronic. See, that's why he got accepted to Washington, whatever state. Isoelectronic. Right. So anything that has the same electronic configuration is isoelectronic. So we don't care whether it's N2 or not. The numbers they should have put up there is the 10. Not N2. They should have put the number of electrons up there. Would have made a heck of a lot more sense. Because anything that has 10 electrons, ooh, that's it. It's going to have that same electronic configuration. We don't care what the diatomic molecule is. And that's how you use this plot. And then it looks a lot better if you draw them like this, though. Okay, so everything up through, I think this is looking like, let's see, it's got the 1 pi, the 2 pi star. Yeah, it's up through this guy, right? Because see, here's the 2 pi star and this order. It's matching nitrogen. So up through nitrogen, or up through 10 valence electrons, we're going to make diagrams that look like this. Okay, and where you got to be careful. Now this is, what I know when I'm looking at this, I see this 2p on this side and this 2p on this side. Okay, they're exactly the same energy, right? So those are both 2p's. But I guess what I'm driving at, well, I think we have to do the homework. I think the homework will be easier to explain it. Let's just leave it at the diagram right now. The diagram is, so for example, if you had nitrogen and nitrogen, the whole thing's N2, right? We've got 2, 4, 6, 8, 10. We've got 12 electrons there. So this must be oxygen then, right? Is that oxygen? Does that count 12?
Yeah, because on the, it's
So
sigma, so it's not pi.
Oh, they did the sigma before the pi? They did?
Right there, yeah.
Oh, they did. You notice that? Oh, thank you very much, Mel. So this is not up through nitrogen. This is oxygens. Thank you. So they did the sigma. Sorry. She said she noticed that right here. They did 3 sigma before 1 pi. See? 3 sigma before 1 pi. It's lower. So they don't really care how much farther down you put it or whatever. All that matters is the order. And all that matters is the order that these are filled and where they're at in height. Are they below the 2p or above the 2p? Below the 2s or above the 2s? Okay? And I guess, like, you can't, if this one is above that one, well, that means you're filling 3 sigma before 2. You just follow this table. You pick your guy that's isoelectronic and follow the order, right? If something has 14, well, then this is the order that you're going to follow, whatever this guy says. Okay? So that's kind of the, and we'll do some of those. I don't think it's near as complicated as I'm making it look. Mel says next chapter is character tables. That means it's going to be a lot of the symmetry stuff. And there's these little operations that you can do to a molecule, and you can't even tell that you did it to that molecule. Like rotating and reflecting, and we'll be messing with all that stuff. But the point is, one of them is given a symbol, a little I. And that means that this molecule has a center of inversion, that in the center of that molecule, you reflect from one side to the other side, it looks exactly the same. Like a sphere has a center of inversion, because if you go from one side and reflect through, it looks exactly the same on the other side. See, like a sphere does, right? Jeffrey's head. I'd say Jeffrey's head. You're the wrestler, and he wrestled, hit the mat most often with his left ear. This got the cauliflower ear. This one didn't. He just lost his center of symmetry on his head. But I guess he doesn't have a chin on top of his head, so that wouldn't work anyway, right? But the point is, see, you have to reflect through the center. So only which one? Homonuclear versus heteronuclear diatomic molecules. Only one of those has a center of inversion. Which one does? Homonuclear, exactly. H2. Only that has center of inversion. So only for homonuclear diatomic molecules are you going to see the little tiny, can you see these little symbols on there? That's a G for Gerada. That's probably more than you need to know. The little U, Ungerada. So on these molecular orbitals, they have the little symbols, the sigmas and the pi's and that kind of stuff, but they also have an additional little symbol, G or U, depending on whether on the center of inversion. When you reflected through, did you get the same thing? So all molecular orbitals have to have G's and U's for what type of molecule? Homonuclear. Now, it's G is if you reflect through that molecular orbital and you get the same thing again. So this would be G. This would be U. What were the colors again? Jeffrey, what were the colors again? It looks prettier with colors.
Changing sign.
Changing sign. They should really just put plus and minus there, because that's what the wave function is doing, is changing sign. But colors look prettier. Okay, so the wave function is just changing signs. But all molecular orbitals for homonuclear diatomic molecules are going to have G's and U's on them. If it's not homonuclear, see here, these all have G's and U's on them because these are all homonuclear. But if I pick something like CO, oh, here's a good one. CO, diatomic heteronuclear molecule. Which one of these columns am I going to use? In other words, I should really use the right terminology. Which is it isoelectronic with?
Did you want for C and
Well, CO is how many valence electrons? 10. 4 for carbon, 6 for oxygen, 10 total. So what up here has 10 valence electrons? Nitrogen. So you better use nitrogens. So scribble out N2, write CO, right? You'd have C on one side, O on the other, right? And get rid of all those G's and U's. But they told you the order. You're good to go. Just make sure you follow that order. Polar bond. Oh, we've had this kind of stuff. What makes it's hetero? Can a homonuclear diatomic molecule be polar? No, because what cancels out? What's the technical word? Yeah, but what generates the partial charge in the first place? What generates the dipole? Electronegativity. You've got this periodic table or this range of these atoms having an ability to hold on to electrons. Some want them a lot more than others. The point is that some are much more closer to being stable than others if it has another electron. Like look at this electron configuration runs the whole gambit. Noble gases have the prime, fantastic, bottom of the well, lowest energy electron configuration you can get. So they're very happy, they're very stable. So the closer you are to that configuration, you use just one more right? Look at fluorine. So very high electronegativity. So that's what makes the polar bond, electronegativity difference. I think we've seen all this. The partial negative charge, that's the whole idea of this. I'd put the partial negative on what? The C or the O? The O. Because it is more electronegative. Is that permanent or does that disappear? That little partial negative. We don't write full negative because full negative means like it's an ion. Is that permanent?
Yes.
Yeah, it better be.
It's always partial negative.
It's always partial negative. Yeah, going away. See if you remember this kind of stuff. HH? Nonpolar. Well, how do you get hydrogen liquid then? You make it cold enough, you can get hydrogen liquid. It's easy for me to imagine this guy as being a liquid or a solid or whatever because right, the little minuses are going to line up with little pluses, right? If they get close enough, they start interacting. And how would you get, does that make sense? How do you get HH liquid? You remember the Quetchers lady? I really liked her explanation. I wish I could have hit record. I don't know if you were awake during this part. Al, you remember it? The Quetchers lady, man, she was bright. Quetchers. But she talked about this. I don't know if you caught it. I really liked her explanation. I can't remember exactly how she said it, but she said that her explanation was like a wave, and I really like it. But the point is what type of forces? Have we talked about intermolecular forces? Starts with a V. Van der Waals. They're also called London. They're also called no, not H-bond. Dispersion. H-bond is super strong, right? So dispersion forces. So, but everything comes down to these dipoles. Everything does. That's the only thing that's going to make stuff stick together. How can HH ever have a dipole? I'm telling you, it has to. That's the only interaction there is. I just don't, stuff doesn't just stick to stuff. I mean, something has to, there has to be an electrostatic plus minus thing going on here. That's it. How can HH get one? HH molecule flying through the air, right? Why doesn't it have a charge right now? Because all electrons are evenly distributed, right? Comes along, she's the wall, bam! No, it doesn't actually strike it. I think her electrons and these electrons are going to repel. They're not going to actually physically strike, right? It's going to get close enough. But it's as hard as a rock. It's going to be like hitting a wall, bam, right? Even though they didn't actually physically, right?
Because the other one's more electronegative than the other one?
Well, isn't that going to mess up the distribution? I'm thinking of like a cotton ball, right? I throw a cotton ball up against a wall or up against Al's head, right? Doesn't it, yeah, it's going to change shape. It'll bounce back right away, but it's going to change shape for a very short period of time. And that very instantaneous dipole is what it is. And that instantaneous dipole propagates like a wave through the entire medium. You get a little plus minus here. Well, then that interacts with this guy. All of a sudden, if you have a little plus minus, now you're going to have more. If this is a plus here, you're going to end up with a minus here. It's going to be automatic. If I have a plus charge going up to this, electrons are going to suck up to it. You have no choice. All from that one collision. It just propagates through the entire medium. Now, it happens very, very quickly, and it's gone like that. It's like a wave propagating through everything. But if you can slow things down enough so that that happens enough, has to happen a lot, it'll stick together, not very well, but it'll stick. It'll form a liquid. Okay.
So we slow down with?
That's why, because slow down, how do you make things slow down? Make it extremely cold, yeah. That's all temperature is. Average kinetic energy. So if you slow things down enough, when you do get that little instantaneous dipole, it will propagate through the entire medium. Things are going to stick together for that one instant in time, but then immediately once it disappears, another collision happens, right? And this is happening all the time. But you really got to slow it down. You maybe even increase the pressure so that they're more closely together. Everything that you already know to generate a liquid. Okay, crank up the pressure. Make it cold. It works. Okay. Looks like we've done some of these. Like, doesn't the number 8 look familiar?
Yeah, we already did that.
13, 14.
Did we do any of the other ones already?
No.
No? All right. So A exercise, number 1. Oh, I've got it written down, hopefully.
What, oh, about the other stuff? This thing. There are definitions.
Oh, this is nice. Why is this a nice question?
What is one of the, oh yes it is. And then give the ground state. Oh, we're just doing valence bond.
Give the ground state, electron configurations, and bond orders. Since they're using the word bond order, we're talking about the molecular orbital theory, an electron configuration. Well, that just means you got to fill one orbital first, then you got to fill another one, and another one, and another one, until you use up all the valence electrons.
Are they given to us already?
Yeah, what's the order? On that chart. Right, and then it told you Li2. Where did it go? Li2. And it perfectly matches. There's Li2. You don't even have to worry about this whole isoelectronic idea. Right?
You heard that, right?
I know, isn't that cool? Do you recognize that sound?
Was it like a chipmunk or something?
No.
Or a bird?
This, I gotta shut this off. This sound, man, you guys should know this sound. Beam me up, Scotty. But this sound had to happen first.
Is it the radio thing? I don't know.
No, the communicators from Star Trek, from the original Star Trek. That's the exact sound from. Yeah, Spock. What'd you want? You never heard that? Oh, Mel.
Oh, that's fine.
Twilight Zone. Okay. So I guess the answer is just going to be. What is that? I can't even read. My eyes are getting so bad. What is that symbol?
Which one?
What is this?
Sigma G.
Okay, so do we keep the G on there?
Yeah.
Yeah. We're done already.
We don't have to write it as, wait, what do we do? Oh, the ground state?
Right, the ground state electron configuration.
We don't have to do the molecular orbital thing?
Well,
Setup?
good question. When they say electron configuration, that's a holdover from when we talked about the Aufbau building up principle with the orbitals, hydrogen atom orbitals. When they want electron configuration, you always said 1s2, 2s2, 2p6, right? We're doing the exact same thing, except using molecular orbitals. Now, when they say draw, where's one? There's got to be one coming up. Draw the molecular orbital energy diagram for, then you got to just sketch it out.
Do you put square because it's homogeneous?
Because there's no, the squares from what? Those superscripts, remember? They are the number of Yeah, number of electrons, right? Sigma can hold, sigmas are just one orbital. Pi's are going to be 2. And the reason why I know that is just from the darn chart, right? Look at my pi.
Oh, yeah, it's two.
Pi's always have 2. Think wherever you draw a pi, you have 2 orbitals. That means you can fill up with 4.
So it's like writing like 1s2, 2s2, but instead of
Yes.
the s, you use the
You have to use the molecular orbitals. And where do you get them from? And where do you get their order? You get them from a table like this guy.
What was the next one?
Beryllium and then carbon. So those aren't so bad. I already gave you the answers.
So we keep the U's and the G's, right?
Yep. But you're definitely going to lose them for this guy when you get to this question. So I don't think this stuff is that bad.
Are you to give this try?
Here's one that Mel was asking about, right? There's one you got to sketch. Oh yeah, don't you have any equation sheet for this? Did I give you one? No? Oh.
Is it on the email?
Oh yeah, I emailed it out. Hopefully I did. But yeah, I'll definitely be giving you that. I'll definitely be giving you this. You just have to know how to use it.
Yeah, he emailed us all of them.
For carbon.
Yeah, I think so.
It was like one folder. Oh, okay. All of them.
So see how many of these problems you can get through.
This is the same thing for number 2. This is the exact same concept of the first one. Just trying to find what it's isoelectronic to.
Yes.
So for carbon monoxide, just be the same as nitrogen.
Carbon is 4, oxygen is 6, that's 10. Nitrogen is 5. Oxygen is 6, that's 11. Do we have something with 11?
It's 10, isn't it? Carbon monoxide. You said it earlier.
That's nitrogen monoxide. I'm talking about this
you
guy.
got B.
Whoop.
No.
You don't have an 11. You don't have 11.
If you don't have an 11, then I would end up, just keep going here. 2, 4, 6, 8, 10.
Let's go up to the next level and put 1.
That's a really good question. He has 10. He has 12.
And there's why you would do it separate. Like C would be one thing, and then O would be the other thing, and they'd be different like types. Remember? And then like it'd be really weird.
Yeah, maybe this is what you're talking about. I need a periodic table. Where is xenon? Xenon is what orbitals? You have 8 from xenon, 7 from fluorine. But xenon has, where's xenon? Yeah, there it is. 1, 2, 3, 4, 5. So when you get down to this one, you've got 5s2, 1, 2, 3, 4, 5. There's 6. Which p is that though? 2p, 3p, 4p, 5p. And then that's the xenon. The fluorine is only 7. We're talking about 1s, 2p, how many? 5, right? Because 5 plus 2 is 7, because you want 7 valence. Okay, you with me so far? So when you make this chart, you have to take this into account. So before I had, like you have xenon on one side, fluorine on the other. So before we had, oh, okay, I've got I have 1s over here, I have 1s over here. But no, you don't have 1s and 1s. What do you have? You have 5s, right? And on fluorine, you have 1s. You better draw that way down here. Because this is supposed to, as you go up, it's supposed to be energy. And then, and all your molecular orbitals are going to be in here. This is where we're going to draw all your molecular orbitals. They're just going to be skewed. Everything's going to be stretched. And then we've got our 5p way up here somewhere. Do you remember playing this? This is what it's going to look like. It sounds like you've done this already. 5p, fluorine's going to be 2p. And that's still below 5s. It should be down, whoop. So the exact where it's at, we're not using rulers and making everything calibrated in the point. The point is that that 2p had better be lower than 5p. That 1s had better be lower than 5s is what I'm going to be looking for. And then all your molecular orbitals had better be in the right order according to whatever it's isoelectronic with over here. And don't have any G's or U's because it's not homonuclear. And you'll get all your points from me. Make sense?
So back to number 2 when we're doing the configuration for a number 11 of a number 11 electron. Do we
Yeah.
just draw
Oh,
the
you know.
energy?
Oh, you know what you do? 11 is isoelectronic. Okay, now what has 10?
Nitrogen.
10 is nitrogen. What is isoelectronic with N2 minus? CO. So that's what I think you got to do. Say that it's isoelectronic with N2 minus. I think that's what I would do. So I'd still be using nitrogens. Or I guess you could say isoelectronic with O2 plus. Wonder what I did to get the right answers. Let me go skip my... I have a minute yet, don't I, Al? Ooh, I can take my time. Yeah, what I said the first time is what works. It's isoelectronic with N2 minus. That works,
Or what is?
right? Because you said 11, right?
I know.
And O is iso. Okay, he put okay.
Does that make sense? Because nitrogen had 10, and then if you have something that has 11, well, if you add a negative to that molecule, you get so.
So that's our configuration for NO. We just one electron and the 2 pi.
Let's see. I may have such a mess here. Let's clean this up. So we're filling up this guy, and we need one more. Yes. And you said 2 pi, not 2 pi g. So good for you.
We don't write no superscript. We just leave it 2 pi. We gotta write the 1.
Oh yeah, yeah. You need your superscript, but you just don't know G or U.